In this video, we will discuss about electrons in metals. So, the particle in a three-dimensional box is an example for electrons in metals. A particle of mass m constrained to move in a fixed region of space. We assume it to be a rectangular box with edges of length ABC. Volume V is equal to ABC. When Vx is 0 when x lies between 0 and A, otherwise infinitive. Vy equal to 0 when y lies between 0 and B, otherwise infinitive. Vz is equal to 0 when z lies between 0 and C, otherwise Vz is equal to infinitive. The three-dimensional Schrödinger wave equation for this system is del squared psi plus 2m by h cross squared into E minus V psi equal to 0. For this particular problem where V is equal to 0 inside the box, the equation takes the form del squared psi plus 2m E psi divided by h squared equal to 0. Del squared value is dou squared psi by dou x squared plus dou squared psi by dou y squared plus dou squared psi by dou z squared plus 2m E psi by h squared equal to 0. In this equation, psi is a function of three variables x, y and z. So this can be rewritten as psi is equal to x, y, z. Differentiating the equation number 3, we get dou psi by dou x equal to yz dx by dx. Further differentiation with respect to x yields dou squared psi by dou x squared equal to yz d squared x by dx squared, and similarly d squared x by dy squared and d squared z by dz squared. Substituting the values in equation 1 and divide by xyz, we get 1 by x into dou squared psi by dou squared x by dou x squared plus 1 by y into dou squared y by dou y squared plus 1 by z into dou squared z by dou z squared equal to minus 2m E by h cross squared. The first term in this equation is a function of x only, the second a function of y only, and the third a function of z only, while the sum of the three is a constant. If each term is equal to constant, we have 1 by x into dou squared x by dou x squared equal to minus kx squared, 1 by y into dou squared y by dou y squared is equal to minus ky squared, 1 by z into dou squared z by dou z squared equal to minus kz squared, where kx squared plus ky squared plus kz squared equal to 2m E by h cross squared. Then now the differential equations in x, y, z coordinates may be written as dou squared x by dou x squared plus kx squared x equal to 0, dou squared y by dou y squared plus kx squared y equal to 0, dou squared z by dou z squared plus kx squared z is equal to 0. The general solution of equation 6 will be of the form x of x equal to ax sin kx into x plus bx cos kx into x, where kx equal to nx into pi by a, where nx is equal to 1, 2, 3, etc. Equation 9 becomes x is equal to ax sin n pi x by a. Applying the normalization condition from 0 to a, integral of 0 to a modulus of x squared dx equal to ax squared 0 to a sin squared n pi x by a dx equal to 1, ax equal to root of 2 by a. Substituting this value in equation 10, we have x is equal to root of 2 by a sin n pi x by a. Similarly, we can solve the equation 7 and 8 to obtain y is equal to root of 2 by b sin n pi y by b. Z is equal to root of 2 by c sin n pi z by c. From equation E is equal to h cross squared by 2m into kx squared plus ky squared plus kz squared, E is equal to h cross squared by 2m into n squared pi squared divided by a squared plus n squared pi squared by b squared plus nz squared pi squared by c squared. E is equal to h cross squared by 8m into nx squared by a squared plus ny squared by b squared plus nz squared by c squared. If the particle is confined in a cubical box in which a is equal to b is equal to c, the eigenvalues of energy are given by E is equal to h cross squared by 8m a squared, n squared plus ny squared plus nz squared. This can be rewritten as h cross squared n squared divided by 8m a squared, where n squared is equal to nx squared plus ny squared plus nz squared. Eigenfunction. If ABC are the length of the box along xyz axis respectively, then the eigenfunction of the particle is psi nx ny nz is equal to root of 2 by a into sin n pi x by a, root of 2 by b sin n pi y by b, root of 2 by c sin n pi z by c. If all the sides are equal, psi is equal to 2 root 2 divided by a into root a sin n pi x by a sin n pi y by a sin n pi z by a, degenerate states. For several combination of quantum numbers, if we have same eigenvalue but different eigenfunctions, then such states and energy levels are called degenerate states. If the state of quantum numbers 112, 121, 211, the eigenvalues are E112, E121, E211 equivalent to 6h squared by 8ma squared. But the corresponding eigenfunctions are psi 121 equal to root of 8 by a cube sin pi x by a and sin 2 pi y by a sin pi z by a. Psi of 112 equal to root of 8 by a cube sin pi x by a sin pi y by a sin 2 pi z by a. Psi of 211 equal to root of 8 by a cube sin 2 pi x by a sin pi y by a sin pi z by a. Non-degeneracy. For various combinations of quantum numbers, if we have same energy in eigenvalue and eigenfunction, then each state and energy levels are called non-degenerate state. If a state of quantum numbers 222, the eigenvalues are E22 equivalent to 12h squared divided by 8ma squared. The corresponding eigenfunctions are psi 22 equivalent to root of 8 by a cube sin 2 pi x by a sin 2 pi y by a sin 2 pi z by a. Thank you.